Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Clearing the cosmic clutter. Tackling space debris for a safer orbit. Space debris, often referred to as orbital debris, is one of the most pressing challenges facing humanity's presence in outer space. These remnants of human activity in orbit range from defunct satellites and spent rocket stages to tiny fragments of metal or paint chips. While each individual piece might seem insignificant, collectively, they pose a substantial threat to active satellites, space missions, and even the International Space Station, ISS. As the number of objects in Earth's orbit continues to grow, so does the urgency to address the cascading consequences of space debris. The origins of space debris date back to the dawn of the space age. Since the launch of Sputnik 1 in 1957, humanity has sent thousands of satellites and other payloads into orbit. Many of these objects have reached the end of their operational life, yet they remain in orbit, serving no purpose. Over the decades, collisions, explosions, and unintentional fragmentation events have added countless smaller pieces to the cluttered environment. Even seemingly harmless fragments, like a fleck of paint, can cause catastrophic damage when traveling at orbital velocities of up to 28,000 kilometers per hour. The issue of space debris is exacerbated by the phenomenon known as the Kessler syndrome, a scenario proposed by NASA scientist Donald Kessler in 1978. This theoretical chain reaction occurs when a collision between two objects in orbit generates fragments that, in turn, collide with other objects, creating an ever-increasing number of debris pieces. Such an event could render certain orbital regions unusable, jeopardizing critical infrastructure such as communication satellites, weather monitoring systems, and GPS networks. While the Kessler syndrome remains hypothetical, recent events highlight its potential. For instance, anti-satellite missile tests conducted by nations like China, India, and Russia have generated significant debris, drawing international criticism. The impacts of space debris are not limited to the objects already in orbit. They also pose challenges for future missions. Spacecraft traveling beyond Earth orbit must navigate through debris fields, increasing the complexity and cost of mission planning. For crewed missions, the risks are even more severe. A small debris impact on the ISS, for example, could compromise its integrity, endangering the lives of astronauts aboard. Space agencies and private companies alike must invest significant resources in tracking and mitigating these threats. Efforts to monitor and manage space debris have been ongoing for decades. Organizations such as the U.S. Space Surveillance Network, SSN, track tens of thousands of objects larger than 10 centimeters in diameter. However, the majority of debris is smaller and remains untracked, despite its potential to cause damage. Advances in technology, including radar and optical systems, are improving our ability to detect and catalog debris, but the sheer volume of objects poses a monumental challenge. International collaboration is essential in addressing the growing problem of space debris. Treaties like the Outer Space Treaty of 1967 and the Liability Convention of 1972 establish basic principles for space activities, but they lack specific provisions for debris mitigation. The Interagency Space Debris Coordination Committee, IADC, comprising major space agencies from around the world, has developed voluntary guidelines for minimizing debris creation. These include measures such as passivating spent satellites and rockets to prevent explosions and deorbiting defunct objects in a controlled manner. However, adherence to these guidelines is inconsistent, and enforcement mechanisms are limited. The rise of commercial space activity adds another layer of complexity. Companies like SpaceX, Amazon's Kuiper project, and OneWeb are launching thousands of small satellites for megaconstellations aimed at providing global internet coverage. While these initiatives promise transformative benefits, they also significantly increase the number of objects in orbit, heightening the risk of collisions and debris generation. Ensuring that commercial entities adhere to debris mitigation practices is crucial to maintaining a sustainable space environment. In addition to preventive measures, innovative solutions are being developed to actively remove debris from orbit. Concepts range from robotic arms and nets to lasers and harpoons, each with its advantages and challenges. The most notable upcoming space debris cleanup mission is ClearSpace 1, scheduled to launch in 2026. This mission, led by the Swiss startup ClearSpace, aims to remove a piece of space debris from orbit. ClearSpace 1 will rendezvous with a discarded Vega rocket upper stage and capture it using a robotic arm. The combined object will then be deorbited, burning up safely in Earth's atmosphere. Similarly, Japan's Astroscale is working on technologies to capture and remove defunct satellites. These initiatives represent critical steps toward addressing the existing debris problem, but they are only the beginning. The issue of space debris is not just a technical challenge. It is also a reflection of humanity's responsibility as stewards of the space environment. As our reliance on space-based systems grows, so does our obligation to ensure that space remains accessible and safe for future generations. Addressing the issue of space debris requires a multifaceted approach that integrates technological innovation, international collaboration, and regulatory reform. While the scale of the problem is daunting, progress is being made in both mitigation and removal strategies. These efforts, however, must contend with socio-political, economic, and ethical challenges that demand coordinated global action. Technological solutions to manage space debris are becoming more advanced, with active debris removal, ADR, emerging as a promising field. Robotic systems designed to capture and deorbit large pieces of debris are under development by agencies like the European Space Agency, ESA, and companies like Astroscale. These systems employ methods such as robotic arms, nets, harpoons, and even adhesives to securely grasp or attach to debris. For instance, ESA's ClearSpace 1 mission plans to target a defunct payload adapter left in orbit from a 2013 launch, using a robotic arm to deorbit the object safely. Similarly, Astroscale has tested magnetic capture technology to retrieve non-operational satellites. While these projects are experimental, they demonstrate the potential for scalable solutions. In addition to physical removal, technologies for debris mitigation are being explored. Lasers capable of nudging debris into lower orbits for atmospheric re-entry are one such option. These systems could be ground-based or space-based, offering a non-contact method of clearing smaller debris. Another approach involves designing satellites with built-in propulsion systems or tethers to ensure they can deorbit themselves at the end of their operational lives. Modern satellite manufacturers are increasingly adopting these measures, particularly as new regulations encourage or mandate debris mitigation practices. However, technical solutions alone cannot resolve the space debris problem. The socio-political landscape of space activities is complex, with no single governing body overseeing orbital environments. The United Nations Outer Space Treaty and Liability Convention provide a legal framework for space activities, but they do not include enforceable mechanisms for managing debris. Voluntary guidelines from organizations like the Interagency Space Debris Coordination Committee, IADC, encourage best practices, but compliance varies. Nations with active space programs, such as the United States, Russia, China, and members of the European Union, have taken steps to implement debris mitigation policies domestically. Still, these efforts must be harmonized globally to be effective. International collaboration is crucial for sustainable solutions. Space debris does not respect national borders, and the actions of one nation or private entity can have far-reaching consequences for all. Agreements on orbital traffic management, shared funding for debris removal technologies, and transparency in space activities are essential. Forums like the United Nations Office for Outer Space Affairs, UNOOSA, and the IADC provide platforms for such discussions, but political tensions can hinder progress. The need for cooperative action is especially pressing given the rise of commercial space ventures, which are introducing thousands of new satellites into orbit. The economic dimension of space debris further complicates the issue. Developing and deploying debris removal technologies is expensive, and the financial incentives for private companies to invest in these solutions are limited. Governments and international bodies may need to establish funding mechanisms or provide subsidies to encourage the adoption of ADR technologies. Insurance premiums for satellites and other space assets could also be tied to compliance with debris mitigation guidelines, creating a financial incentive for responsible behavior. Ethical considerations also come into play. Decisions about which debris to remove and who bears the cost raise questions of equity and responsibility. Developing nations, for example, may have limited access to space yet still suffer the consequences of debris generated by spacefaring countries. Ensuring fair access to a sustainable orbital environment is a challenge that requires global consensus. Public awareness and advocacy can also drive change. Space debris, while a technical and policy challenge, is fundamentally an issue of environmental stewardship. Drawing parallels to terrestrial environmental movements can help build public support for sustainable practices in space. Highlighting the risks to essential services, such as communications and weather forecasting, can underscore the urgency of addressing this issue. In the long term, managing space debris will likely involve a combination of preventive measures, active removal technologies, and robust international governance. As humanity's presence in space continues to expand, so too must our commitment to safeguarding the orbital environment. By investing in innovative solutions, fostering international collaboration, and embracing our shared responsibility, we can ensure that the final frontier remains a viable and accessible domain for future generations.